In the last session, we learned about lenses, convex and concave, and the image formation and the characteristics of the image. In this concluding session, let's learn about the lens formula and the magnification formula, and also let's do some problems involving refraction as well as reflection. Let's first start with how do we measure the focal length of a lens. It is easy to do that with a convex lens because it forms real images. One approximate method is making use of the fact that the image of a very distant object at infinity is formed at the focal point. So we take our lens near a wall and obtain the image of a faraway object like a tree. The rays will nearly be parallel and the image will be formed on the screen inverted. If you can obtain the image on a screen, it must be real. And if it is real, it will be inverted. Now adjust the position of the lens so that you obtain a very sharp image and then measure the distance. Put a scale here and measure the distance. That will be the focal length of that lens. But this is approximate. More accurate methods using a plane mirror. So we take a pencil and we have a vertical scale over here. You have a vertical scale over here. We put the lens here, we can adjust the position of the lens, and we also have a plane mirror. We adjust the position of the lens such that we obtain the image of the pencil here exactly at the same location. That means the image of this point of the pencil is formed at the same point. That means the image and object positions coincide. Coinciding means what? That whichever ray went away from that point came back to the same point. It retraced its path. How will that happen? A ray that goes like this hits the plane mirror. Now it must retrace its path. Therefore, it must fall perpendicularly on that mirror. Then only it will retrace. And then it comes back to the lens and it retraces its path. Now these rays which are now hitting the lens are parallel to the lens, and if they're intersecting here, then this distance should be the focal length. But we have to make sure that there's no parallax when we see the pencil object and the image. When we see from any location, we see there should be no parallax. Then we can read off this focal length. Second is called a UV method. There's a relationship between object distance and image distance. We put a candle, we obtain the image of the candle on the screen, which will be inverted. We measure this distance, and there's a lens formula to tell us the focal length. What is the lens formula? 1 by V minus 1 by U is equal to 1 by F. In the case of mirror, this was a plus sign. That's a difference here. And what is the lateral magnification formula? M is always HI by HO. In this case, it is plus V by U. If you remember, for a mirror, it was minus V by U. So essentially, same structure as a mirror, but the signs are changed. What about the sign conventions? Well, exactly the same as we did for mirrors. All distances are measured from the optical center. If you are going against the direction of the incident ray, such a distance will be negative. Like in this case, there is an object here, the incident ray is from left to right. The object distance will be negative because you are going against the incident ray. If the image is formed here, then that image distance will be positive because you are going along the incident ray. And the second thing is any distance above the principal axis is taken as positive and a distance below the principal axis is taken as negative. Same sign convention as for the mirror. Focal length of a convex lens is positive because you are measuring that focal length from the optical center and going towards the focal points. You are going along the direction of the incident ray. The focal length is positive. Whereas for a concave lens, you're going against the direction of the incident light. Now, this mirror and lens, I want to put things in perspective. Converging devices and diverging devices. Converging devices, concave mirror is converging, convex lens is converging. In diverging devices, convex mirror is diverging. You can see rays diverge, and a concave lens is diverging. Now, focal length. Just now we said that the focal length of a convex lens is positive, but the focal length of a concave mirror is negative. The focal length of a concave lens is negative, and the focal length of a convex mirror is positive. So, at least one thing you can see that as far as the focal length is concerned, concave mirror, concave lens, both of them have got negative focal length, and convex lens and convex mirror, both of them have got a positive focal length. That similarity is there. But concave mirror is converging and convex lens is converging. Convex mirror is diverging and concave lens is diverging. Furthermore, we can write in terms of mirror formula. Mirror formula is 1 by V plus 1 by U is equal to 1 by F, and the lateral magnification is minus V by U. The same thing for a lens. The sign changes. 1 by V minus 1 by U is equal to 1 by F, and the magnification formula is plus V by U. Putting things in perspective. Let us do some questions now. A concave lens has a focal length of 15 centimeter. At what distance should the object from the lens be placed so that it forms an image at 10 centimeter? And what is the magnification produced by the lens? So F is given, U is supposed to be found out, image is, distance is given. Concave lens, the focal length is negative. That is the first thing. Don't make a mistake in sign convention. The image distance is 10 centimeter for a concave lens. Now, for a concave lens, the image is formed on the same side of the lens as the object is. So remember, this is the concave lens. If a ray comes like this, it diverges and the image is formed on the same side. So the image distance is also negative. Now apply the lens formula. 1 by V minus 1 by U equal to 1 by F. We are supposed to find U. So 1 by U is 1 by V minus 1 by F. V is minus 10 centimeter. F is minus 15 centimeter. That makes it plus. Minus 1 by 10 plus 1 by 15. Take LCM as 30. Minus 3 plus 2. That is minus 1 by 30. So U is minus 30 centimeter. That is the position. That means the object was somewhere here at a distance of 30 centimeter. Magnification is plus V by U. V is minus 10, M is minus 30 plus. Again, M tells us a lot of things. The sign tells us whether it is erect or inverted. That plus means that it is erect. And erect means virtual as well. So I should say erect and virtual. And diminished, this number itself, if it is less than 1, it means it is diminished. It just confirms concave lens always produces diminished images. Next, the height of an object is 2 centimeter. It is placed perpendicular to the principal axis of a convex lens, this time of focal length 10 centimeter. Distance of the object is 15 centimeter. So U is known, F is known, and HO is known. Find the nature, position, and size of the image and also its magnification. This is a convex lens, so f is plus 10 centimeter, u is minus 15, and ho is plus 2 centimeter. So first of all, where is the image located? 1 by v minus 1 by u is equal to 1 by f. That is the lens formula. Bring 1 by u to the right, it becomes plus. U is minus 15, f is plus 10, LCM is 30 once again, it is minus 2 plus 3, it is 1 by 30, so V is plus 30, that means on the other side of the lens. M is V by U, V is plus 30, U is minus 5, so minus 2. Minus means inverted, inverted means real, and 2 means twice the size of the object. So nature is real and inverted. Position is 30 centimeter on the other side, and size, okay? If I just talk of size, M is equal to HI by HO, therefore HI is equal to MHO. I'm just talking of the size. So M is 2 and HO is also 2, so 4 centimeter. That is the size of the image. Now, let's talk about power of a lens. If you're using spectacles, you would know that you have a certain power. Typically, it would be a negative power because you are using a concave lens, and that is there to correct your myopia. We'll talk about the human eye and defects of the eye in the next chapter. So what is power of a lens? It implies the ability to converge or diverge a beam. How much are you bending the light, either converging or diverging, but how much are you bending? If you are bending it a lot, then you are powerful. So see here, suppose I take a convex lens. The concept applies to any type of lens. Suppose I take a convex lens, a ray parallel to the principal axis will go and hit the focal point. If it bends like this, that means it is from its original direction, it is bending a lot, so that is high power. If it is bending less, that is lesser power. And if it is not bending at all, then that is zero power. Clearly, if it is high power, then the focal length is small. Small focal length implies high power. The definition of power of a lens is it is always in a certain medium. Now, normally it is air, but the definition is refractive index of the medium divided by the focal length in that medium. That is a definition. And in air, the refractive index becomes 1, then the power is 1 by F. Okay. Now, when the focal length is expressed in meters, then power will be, dimensions of power will be 1 upon meter, but we give a name called diopter. And power will have the same sign as a focal length. So suppose I say the power of a lens is plus 1.5 D means diopters. Focal length is also positive, that means it is a convex lens. If I say power is minus 2 diopters, it means it is a concave lens. Your power, if you are using spectacles, I can say it must be negative. Okay. So we do say power is equal to 1 by F, but that is only for air, and that is a usual situation. But power depends on what is the refractive index of the medium as well. For air, it is 1. And if the focal length is in meters, then the power is written as diopters. So whenever you have to write power, make sure that you have converted the focal length in meters. Otherwise, you will get a wrong answer. If you have two lenses in contact, then the powers are added up. Suppose I have two convex lenses of focal lengths f1 and f2, then this combination will have a certain focal length, let us say capital F. then the relationship is 1 by capital F is 1 by F1 plus 1 by F2 with the appropriate sign. Don't forget the sign of F1 and F2 with the appropriate sign. But 1 by F in air, okay, that is in air, I can say 1 by F is the power, so power is added up. Even if you have different types of lenses, power is still added up. Now, for this one, the power will be positive because it's convex, the focal length is positive. For this one, the power will be negative because it is concave and the focal length is negative. Whatever it is, simply add up. If you get a positive sign, that means then the combination is acting like a convex lens. If you get a negative sign, it means it is acting like a concave lens, the combination. In general, you can put whatever many lenses in contact, the powers are just added up algebraically, taking into account the sign of each power as well. So let's take a case of refraction and reflection. An object is placed 15 centimeter to the left of a convex lens. This is the object 15 centimeter to the left of a convex lens of focal length 10 centimeter. A convex mirror is placed to the right of the lens at a distance of 10 centimeter. So this distance is 10 centimeter. The focal length of the convex mirror is unknown. We have to find that out, but the data is also given that it is found that the final image by the combination coincides with the object. Again, coinciding of an object and image means the ray retraces its path. Image coincides with the object means ray retraces its path. Now, first event occurs here, that's a refraction. Second event occurs here, which is a reflection. And the ray comes back. So third event also happens at the lens, which is a refraction. So if I start with the lens first, the U is minus 15, the F is plus 10. The image formed by the lens using the lens formula 1 by V is 1 by U plus 1 by F. U is minus 15, F is plus 10. I get V is equal to plus 30. So the ray starts after the refraction from the lens, the ray goes and it would have formed an image here at a distance of 30 centimeter. That is I1, let me call it. Image formed by the first event. But then I also know that the ray retraces its path. If the ray is retracing its path, then it must be falling perpendicularly on this convex mirror. That means this line that I have drawn dotted here at this point is the center of curvature of the mirror. Right, now I know the answer. This is 10, so from here to here is 20. The radius of curvature of the convex mirror is 20 centimeter. The focal length is 10 centimeter, R by 2. For a mirror, R by 2. And plus, because it is a convex mirror, plus 10 centimeter. And after the second event, it retraces its path, and since it is coming by the same path, it again retraces its path. Therefore, the final image is formed at the object itself. Another question. In this arrangement, now we have a concave mirror and a convex lens. Focal length is 15 centimeter, object is placed 20 centimeter. It is found that the final beam comes out parallel to the principal axis. What is the focal length of the mirror once again? So if it is emerging parallel to the principal axis, is the final one, then that means this ray that is coming, that's for the third event, is the first event, there's the second event, and there's the third event. For the third event, the ray is coming from the focal point of the lens. Okay, so let's work out. For the lens, for the first event, U is minus 12, F is plus 15, and using the lens formula 1 by V is equal to 1 by U plus 1 by F. U is minus 12, F is plus 15, LCM is 60, I get minus 1 by 60. So therefore V is minus 60 centimeter, minus. So that means I1, the image formed by the first event, is at a distance of 60 centimeter. This I1 is the image formed by the lens, which I'm calling the first event. Now, in general, when a ray of light goes through multiple events, then the image formed by the first event acts as the object for the second event. The image formed by the second event acts as the object for the third event, and so on. So this I1 is actually O2 as well, object for the second event. So mirror is the second event now. The U now is 60 and this is 40. So U is minus 100 centimeter for the mirror. Now what is this V? The image formed by the mirror. I'm straight away writing minus 25 centimeter. I'm straight away saying minus 25. Why do I say so? Because I know that for the third event, this ray that is hitting the lens should have come from the focal point of the lens. Now the focal length is 15, so this is 15, so therefore this is 25 centimeter from the pole of the mirror. So the image formed by the second event is forming here, and that is why V is minus 25. Now the mirror formula is plus 1 by V plus 1 by U. Don't make a mistake. So we had to find F. 1 by F is 1 by V plus 1 by U. V is minus 25, U is minus 100, LCM is 100, minus 4, minus 1, minus 5 by 100. So minus 20 centimeter is the focal length of the mirror. So you should be able to handle multiple events using simple logic that the image formed by one event acts as an object for the other. That is a guiding principle. And then look at the data. They will be telling you something about where the final image is formed or something else that they might be telling you. You have to work out step by step. So to summarize, diffraction as a chapter, light travels in straight lines but only within a homogeneous medium. And also provided that there are no slits or holes or obstacles that are very small. If there are any slits or holes or obstacles, those should be very much larger than the wavelength of light, then light travels in straight lines. As long as the medium is homogeneous, it is not changing its optical properties. As long as any obstacles or openings in its path are not too small, the light goes like a good boy in a straight line. But if the obstacles or the openings becomes extremely small, then wave nature of light comes in and the ray bends, diffraction, etc. starts happening. We're not talking of diffraction right now. Let's talk of heterogeneous medium, that if the medium properties are changing, then the diffraction will happen and light will bend. But that bending occurs only at the interface. After that, no bending. So a ray of light comes, bends at the interface, and then goes straight. It doesn't keep on bending. Mirrors and lenses form images, and images can be real or virtual depending on the position of the object. For spherical mirrors, for instance, we have seen that images can be real or virtual. For lenses also, images can be real or virtual, depending on the position of the object. That was not the case for a plane mirror, though. For a plane mirror, irrespective of the position of the object, the image is virtual, and same size also. Reflecting surfaces of all types obey the laws of reflection. Refracting surfaces obey the laws of refraction. Cartesian sign convention are followed for spherical mirrors and lenses, and never ever make a mistake in sign conventions, including for focal length and radius of curvatures. Mirror formula is 1 by V plus 1 by U is equal to 1 by F. Focal length of a mirror is r by 2, radius by 2. Lateral magnification produced by a spherical mirror is hi by ho, but that is also true for lens. But the mirror formula, the lateral magnification formula for a mirror is m is equal to minus v by u for mirror. And this was f equal to r by 2 for mirror, not for a lens. Furthermore, a light ray that travels obliquely from a rarer to denser medium bends towards the normal, and if it goes from denser to rarer, it bends away from the normal. It should be oblique. If it is perpendicular, it doesn't bend at all. Light travels in vacuum with a very large speed of 3 into 10 to the power 8 meters per second, and the speed of light in any other medium is lower than this. Different colors of light have the same speed in vacuum, but they have different speeds in another medium. Only in vacuum, all colors have the same speed. When they enter some other medium, they will slow down, but the extent of slowing down is different for different colors. Violet slows down the most, red slows down the least. Therefore, the refractive index for violet is more than the refractive index for red for a given medium. The refractive index of a medium is the ratio of the speed of light in vacuum to that in medium, that is n equal to c by v. In case of a rectangular glass slab, the refraction takes place at both air glass and glass air interfaces, and the emergent ray is parallel to the direction of the incident ray. Lens formula is 1 by v minus 1 by u is equal to 1 by f. Power of a lens is the reciprocal of its focal length as long as you are talking of air as a medium, and the SI unit of power of a lens is diopters. Furthermore, the lateral magnification formula for a lens is plus V by U. So those were the points for refraction, and that completes this chapter. So please go ahead and do the questions in your school textbook and then the assignment that is available within the course material. So we have done mirrors, that is reflection, then we did refraction, and the third chapter on this topic of optics is called Human Eye and the Colorful World. That will be a focus in the next session, and after that, we will be completing optics.